So in this unit, we're going to start talking a lot about different types of energy and how those energy affect our reaction and all of that stuff. So to start off, we're going to start with some definitions here. We're also going to be looking at different types of graphs throughout this unit and the next couple. But we really need to focus on these important definitions. They are crucial to our study of energy, but they're also kind of difficult to wrap your head around at first. So let's take a little bit of time to go through them. An endothermic process is a process or a reaction that takes in energy. That means that whatever reaction this is, it requires more energy than it has. It needs to get that energy from somewhere, so it brings it in from the outside. We have something called the law of conservation of energy. Just like the law of conservation of mass, it says energy cannot be created or destroyed, but you can move it from one place to the other. So if we need energy to go into the system, we need to take it from the surroundings. The system in this case, you can think of them as the actual chemicals or substances. The surroundings will be the water that the substances are dissolved in, the beaker that the reaction is happening in, the air around it, anything like that. Okay, so any of that stuff can give the system more energy. So a lot of our graphs are going to be looking at what's actually happening to the system, but us as humans, everything we can observe is what's happening to the surroundings. So it's a very important distinction that you need to kind of get through to understand this concept. So when we look at these different types of graphs, especially in the next unit, when we look at potential energy diagrams, you're going to see the energy of an endothermic process will go up because it's taking in energy. But everything else is going to say that it's cold. If you touch the beaker, it's going to be cold. If you take the temperature with a thermometer, it's going to be cold because you're taking the temperature of the water. And we just said the water counts as surroundings. Okay, so it's going to be cool to the touch or thermometer. Exothermic is the opposite. An exothermic process releases energy into the surroundings. So that means the system itself, the chemicals, are going to lose energy, but everything that we can observe, the surroundings, are going to gain energy. So it's going to be warm to the touch or a thermometer. Okay, so when we get to those potential energy diagrams, you will see that in exothermic process, the actual system, the chemicals are losing energy. You will see that in the graph. But here, when you're touching it or taking the thermometer, it's going to appear warmer because as humans, we are just going to be able to do observations of the surroundings. So those are just two very important definitions that I like to get out of the way at the beginning of this because this is the first time we're really talking about heat and how it affects our reactions. So this is a heating curve, okay? This is not the potential energy diagram I was just talking about. In this, we are taking the temperature with a thermometer, okay? So that is different than the potential energy diagrams, which we'll get to later. So this is an actual thermometer. This is the surrounding. So what you will have here is I'm going to label my different phases. And you can see they already are labeled kind of. So this is going to be a solid phase because it's low temperature. I think that we are heating it like on a hot plate. This is going to be liquid. And this is going to be gas. In between, that's where melting happens or boiling or evaporation happens. So you have a little bit of both. Here we would have solid and liquid, and here we would have both liquid and gas. We also want to talk about the energy types and what's happening to them. We have two different types. Ke is kinetic energy, and Pe is potential energy. Kinetic energy is directly related to temperature. So kinetic energy goes with temperature. So when temperature changes, the Ke changes. So on all of these diagonal lines, the KE is increasing. On the horizontal lines, the potential energy is increasing. And that's not related to temperature, so that is why it doesn't go up. So if you're heating this up, you're not going to like take it off the hot plate. That's not what's happening here. It's that our heat energy that we're having from the hot plate is being converted into whatever energy the system needs at that point. So our heat energy is constant. And you will see that it is converted into kinetic energy here, so it can make the solid get to the melting point. And then it's converted to potential energy, so the solid can turn into liquid. Then it's kinetic energy so that the liquid can get to the boiling point, and then it's potential energy so that all the liquid can turn into gas. And then last part, once it's all gas, it starts getting evaporated. It all is going, obviously it's getting heated up. It's evaporated already. So 2 more things I want to label on here. We just kind of referenced them here. This right here is where the melting point is. Or freezing point, same thing. And this right here is where the boiling point is. So you know that once this, for example, once this liquid hits the boiling point, it's going to stay there for a little while so that all the liquid can become gas. Now, a cooling curve is the same thing, except it's getting colder. So it starts as a gas, then we have liquid in the middle, and then we have solid at the end. In between here, we have gas and liquid and solid. We can also label the kinetic and potential. So here, KE is decreasing on all the diagonal lines. And then our horizontal lines, we have PE decreasing. Now, if you just had a horizontal line, it would be difficult to tell what the PE was doing, okay, because it's just going to be a horizontal line. So you have to look at the overall curve to see what happens. So you have to look what happens before and after the horizontal line. If it's going down, the PE is decreasing on that horizontal line. If before and after it's going up, then the PE is increasing. So you just have to use kind of your context clues here. And then our last thing we want to label here, this is going to be the boiling point this time. And this one is the melting point or freezing point. They are the same. So that's really it, how to read a heating or cooling curve.